Hello, we are continuing with random process. The topics to be discussed are what is noise, signal to noise ratio, figure of merit, types of noise, power spectral density derivations, noise in communication system, receiver model for the linear modulation, figure of merit for linear modulation, baseband receiver, coherent demodulation, noise in single sideband suppressed carrier wave, and the envelope detection. Now the first question comes in mind, what is noise? Noise is an unwanted signal as shown on the right hand side, a spurious fluctuations of the magnitude with respect to time, which are noise. These noise are commonly generated within the device, or it is superimposed to the signal when the signal is traveling in the transmission line in the channel. So such a noise limits the operating range of the system. Noise is indirectly places a limit on the weakest signal that can be amplified by an amplifier. The oscillator in the mixer circuit may limit its frequency because of noise. A system's operation depends on the operation of its circuit. So noise limits the smallest signal that a receiver is capable of processing. Noise also affects to the sensitivity of the receiver. When it affects, because sensitivity is nothing but the smallest amount of input which produces the quality output. So if the noise is contaminating the message information, then such a calibration of the system is destroyed. The signal to noise ratio, figure of merit are important parameters for the communication system. Signal to noise ratio is nothing but the ratio of the signal power to the noise power when a system is produced or system is readied for the market. The figure of merit is also another important parameter for communication system. It is the ratio of the output signal to noise ratio to the input signal to noise ratio. Additive wide Gaussian noise, which is added in the channel when the signal is traversing through the channel. So therefore, the signal does not have any control to avoid such an addition of the noise. So such a noise is additive in nature, but why it is white? Because we are considering all frequency components. That is why it is white in nature. So the amount of contamination for several frequency may not be same, but as the frequencies are involved, all frequencies are involved. That is why we are considering the noise is white in nature. And why it is Gaussian? Because the distribution of the power spectral density of the noise is following the Gaussian distribution. Therefore, additive wide Gaussian noise is the basic noise model which is required for the calculation of signal to noise ratio in case of any communication system. The noise is normally of two type of nature, either external source or internal source. External source means when the noise is traveling through the transmission channel, it is induced by the external noise, and when the signal is propagating through the device, that means when it is processed through the device, at that time device fluctuation, that is electron fluctuation with unwanted voltage, may produce such unwanted signal within the device known as the internal source of noise. The types of noise are normally of two types: external source of noise such as the atmospheric noise, extraterrestrial noise such as the solar noise, cosmic noise, as well as industrial noise. And internal source of noises are thermal agitation noise, short noise, transit time noise. Normally short noise are produced due to the random movement of electrons and holes. The thermal agitation noise are also called Johnson noise or electrical noise. The transit time noise are produced during the transition. Also due to branching operation of the current, noises are produced. There are some miscellaneous noise which is another type of noise that includes flicker, resistance effect, as well as mixer generated noise. The power spectral density is one of the important characteristics in the signal system. If we integrate the power spectral density in the range of frequency, we can calculate the spectral power. So for the system design issue, power spectral density is having a great important role. To derive the power spectral density, the mathematical calculation which can be carried out are following Einstein-Wiener-Khinchin theorem. So in this theorem, it is telling that the autocorrelation function and the power spectral density are the Fourier transform pair. The noise in the communication system is an important part of the calculation to design the communication system. Normally, this noise in communication system is required to analyze the noise performance of the modulation schemes. The results of our analysis will show that under the certain conditions, frequency modulated signal is superior to the linear modulation schemes incubating noise. To analyze the noise performance of various continuous wave modulation schemes, performance of the detector or demodulator and a suitable receiver model need to be investigated. A typical receiver model for the linear modulation system is shown on the right hand side. Now here, if we observe, a receiver model receives the signal from the antenna, which is processed through the radio frequency amplifier and fed to the mixer. In the mixer, the local oscillator signal is also applied as input. So local oscillator signal should be tuned to the same carrier frequency of the modulated signal, as well as it should be in phase with the incoming signal. The resulting mixer output will be fed to the intermediate filter, that is IF filtering, and thereafter the output of this IF filter will be processed by the demodulator, so that the baseband amplifier will amplify the baseband signal, and which will be fed to the transducer for generating the physical parameter variations. So equivalent block diagram of such a receiving model is shown below, where the signal ST, which is fed to the channel acts as an adder, which adds the additive white Gaussian noise to the signal, and this resulting signal is passed into the equivalent IF filter, intermediate frequency amplifier. So this IF filter processes the signal which is demodulated and low pass filtered for the intended application. Now here the noise assumed are white Gaussian noise with power spectral density N0 by 2, which is equally distributed on both the side of the frequency axis. We treat this HEQF, that means the transfer function of the IF filter, to be an ideal narrowband bandpass filter with a passband between Fc minus W to Fc plus W, because the 2 times of W is the bandwidth of the system. That is, modulated signal is having the bandwidth 2 times of W, where W is the message bandwidth. Normally lower sideband refers to Fc minus W and the Fc plus W refers to upper sideband. The transition bandwidth Vt is the 2W for both double sideband modulations schemes. So and W is the message bandwidth, and it is also the bandwidth of the single sideband suppressed carrier signal. In the present context, the carrier frequency is Fc, and which is measured as the intermediate frequency, because the carrier frequency is reduced to the intermediate frequency, that is IF frequency, by the IF filter. So overall the modulated signal remains same. Only thing is that carrier frequency is reduced to the IF filter frequency, where IF stands for the intermediate frequency, which is nothing but the difference of the local oscillator frequency and the carrier frequency. Now, such a frequency decrease at the receiving circuit is required because prior to the demodulation, if we decrease the carrier frequency, then the filter design will be easy. At higher frequency, the filter design becoming expensive as well as inaccurate. So if we decrease the carrier frequency by using the intermediate frequency amplifier, then the filter design as well as the amplifier design will be easy as well as less complex. The figure of merit for the linear modulation is nothing but the ratio of the SNR0 and SNR at the receiver input, which are defined in this way, that signal to noise ratio at the receiver output is the ratio of the average power of the message at receiver output to the average noise power at the receiver output. Similarly, SNR at the receiver input is nothing but the ratio of the average power of the modulated message signal at receiver input to the average noise power in the message bandwidth at receiver input. The baseband receiver design is the optimum target for any communication system, and the equivalent model is shown on the right hand side, where the channel is acting as a adder, which is taking the message as well as the additive white Gaussian noise as input, and the resulting signal is fed to the low pass filter for output. So this is the scheme which is termed as baseband receiver, because baseband receiver does not have any modulated signal. Now, if XT be the real narrowband bandpass linear modulated DSB signal, then XT can be expressed as the difference of the in phase and quadrature component. So the envelope capital AT and the phase can be derived from the amplitude modulated signal equation. So here the column which is showing that explains the important electrical characteristics of the modulated signal and the detector. So here the type of the ideal detector to which XT is input and the detector output proportional to which parameter are explicitly shown. So first is the coherent detector, which is showing that the detector output is proportional to XCT, that is the in phase component of the signal. Similarly, the envelope detector is proportional to the envelope magnitude of the modulated signal. The phase detector produces the detector output which is proportional to the phase of the modulated signal, and the frequency detector produces the slope of the phase which is proportional to the message. Noise in double sideband suppressed carrier is another important observation which is shown on the right hand side, in which the signal mixed with the white Gaussian noise are passed through the filter, and then it is applied to the multiplier where the local oscillator mixes with the incoming signal, and finally the signal is passing through the low pass filter. So the portion which is marked using the dotted line is known as the coherent detector, which is producing the output, and this output is proportional to the message signal. Noise in double sideband suppressed carrier wave can be further carried out, where PM denotes the message power, and this can be easily calculated from the power spectral density of the message as shown by the equation. Similarly, the output signal power can also be found out by integrating the power spectral density of the receiver output signal. So both are having the signal power, but in the receiver output there is some scale factor AC square by 2 are coming out. Therefore, we can adjust the scale factor to unity so that the original signal power can be reduced, can be resolved at the output of the DSB-SC demodulator. Now, signal to noise ratio at the receiver input and the signal to noise ratio at the receiver output both are calculated separately. And for the DSB-SC, it has been shown that the figure of merit is equal to 1. If we see at the single sideband suppressed carrier, then we will understand that only one of the sideband which is transmitted in case of double sideband suppressed carrier are transmitted. But why it is so? Because in case of double sideband suppressed carrier, we are sending the two number of sideband, whereas in case of single sideband suppressed carrier, we are sending one sideband, because one sideband is sufficient to transmit the same information. So why should we transmit two sidebands separately? So it is a wastage of power. So that is why in SSB-SC we are taking the advantage of sending only one sideband, and such a single sideband suppressed carrier signal can be expressed in terms of the message signal and its Hilbert transform. Hilbert transform is nothing but the 90-degree phase shift of the message signal, and such a signal is represented by ST. This is the one sideband signal, single sideband signal. So generalizing the ST, further we got another expression, and finally the autocorrelation function of the single sideband suppressed carrier signal has been found out, so that we can find out the power, because we know the Fourier transform of autocorrelation function gives us the power spectral density. So in this way we can find out the signal to noise ratio at the input of the receiver for the SSB-SC signal, and further we can carry out the investigation to find out the signal to noise ratio at the receiver output, and it shows the figure of merit for the single sideband suppressed carrier is equal to 1. The envelope detection of the amplitude modulated signal is used, which is a non-coherent receiver. So double sideband full carrier amplitude modulated signal requires envelope detector for the demodulation process. Here it is explicitly shown that the amplitude modulated signal ST is given by AC into 1 plus GM into MT into cos omega CT. So from this we can calculate the average power of the modulated signal, and thereby we can calculate the signal to noise ratio of the double sideband full carrier signal at the receiver input, as well as the same could be carried out for the receiver output. So envelope detection process can be plot on a triangle from which the hypotenuse shows the resultant signal, and if we calculate the signal to noise ratio from this hypotenuse, we can get the figure of merit, which is given by the ratio of the square of the modulation index to the denominator, which is square of the modulation index plus 2. And from this equation it's very much clear that as the modulation index is having the highest value 1, therefore the figure of merit for the double sideband full carrier signal is not greater than 1 by 3. Therefore 33.33% is the figure of merit for the double sideband full carrier signal under the 100% modulation. Now why this is so? This is happening only due to the presence of the unmodulated carrier signal in the DSB-SC waveform. Such a signal does not carry message, but it is present, it is wasting the power. The wastage of power in the modulated signal due to unmodulated carrier transmission is one of the disadvantage of double sideband full carrier transmission. That is why double sideband suppressed carrier is having more advantage by suppressing this unwanted carrier, and that is why the figure of merit can be increased to 1 for double sideband suppressed carrier. But still one more disadvantage you have observed, because one of the sideband is sufficient to transmit the message. That is why out of two sideband, if we suppress one sideband, then another, the single sideband suppressed carrier signal can be formed, and therefore we can easily transmit the single sideband suppressed carrier signal with a figure of merit unity, as well as the wastage of power has been reduced to the low level.